So what I have here is a sequence peak generator, and a sequence is just a sequence of positive integers. It allows a 13-bit input, so it's a maximum of 4192. And a sequence is terminated when there's a 0 input. And what this does is it basically takes in the sequence, and when there's a 0, it outputs in the LED display what was the highest point in that sequence. So for example, if you have 1, 2, 3, 4, 5, and then I put in a 0, then it outputs a 5. So how it works is that first there's an input first it works with an input module. So for example, if I try to put in 1, 2, 4, if I try to put in 7, then and if you press the center button, then the input module basically inputs that 7, right? So the input module outputs that 7 into the comparator, and the comparator is not your basic comparator. It's a slightly modified comparator that outputs the highest point in the sequence whenever the input module spits out a 0, right? So for example, right now the comparator has a stored value of 7 because I put in a 7 here. But if I switch off this one, now it's just a 6, then I put it in here, then the stored value is still a 7 and not a 6. However, if I put something like 16 here and I try to enter it, you can't see it now, but the comparator now has a stored value of 16. But if I put it in as a 0, then it will start doing all of the calculation and the LED display as well. So I was able to make this work with a finite state machine, a pretty basic one. And the reason why I needed to do that is because the double dabble algorithm, which I will explain later, and the LED display should only be activated whenever the output is 0. So I needed that extra functionality. Now if I try to press this center button with a 0 as the input, the 16, which is our stored value right now, is going to be outputted, and then it will be an input to the double dabble algorithm, which basically converts my binary value into BCD, which is, instead of, like, for example, if I needed the integer 10, then I need a 0000 and then a 0001 to say that, hey, this needs to be 1 and this needs to be 0. In this case, the 16, the 10000, needs to be a 1 here and a 6 here. So the double dabble algorithm, the code that I got from the GitHub, is a clock process, and I'm pretty sure it has like 16 flip-flops in it for 16 shifts, and the procedures for the double dabble algorithm, which you can search up. But when you press this button, it becomes 16. And that double dabble module is connected to a basic display code that basically displays this with an adjustable refresh rate. So I'm not too experienced with static timing analysis, but I did do a timing summary with only the main clock as the only source clock. I'm not too familiar with what the right input delay or output delay is, but as of now, it does pass timing analysis, although I'm not too sure how important timing analysis is for a basic project like this. But yeah, this is basically how it works. As you can see, we can display it again. Now we want to put it in a new sequence. So for example, if you want to put 1 here, input that, and then put in a 0, it will be a 1. If we want to test out like insane values, for example, this is the highest it can go since it's 13-bit. I mean, the highest it can go is all of these as 1s. So let's just try that out. Input that, and then make everything light up, and then let's make everything off. That's a 0, and it outputs 8191. It's pretty basic. One of my first mini projects with the Basis 3 FPGA, and yeah,